Hello and welcome in. We are here starting a new chapter. Chapter 5 is on our acid and base chemistry in the context of equilibrium. In this chapter, we'll introduce our acid-base definitions, a whole variety of definitions, and we'll get into some nice equations for calculating pH, pOH, how acidic or how basic our solutions might be. All right, we'd like to start here with just some definitions about our acids and bases. The first definitions that we'll start with are the Arrhenius definition. So according to the Arrhenius definition, an acid is going to produce H plus when it's in solution. You can see that on our slides here. We have some acid molecule. This little blue circle up at the top is our H. Once it's in the solution, that H plus will dissociate from our counter ion. In this case, we have H plus and chloride or hydrochloric acid. There we go. H plus being produced in our solution. If we have an acid like this, all right, it behaves as we expect acids to behave. They tend to taste sour. Right? A lot of foods are acidic. We can use them to dissolve metals, and we have some ways to indicate that we have an acid present. One of them is litmus paper. Litmus can turn red to show that we have an acid. Now, when our acid produces that H+, here we saw that picture, what actually happens in water is we have tons and tons of solvent molecules, water molecules, also present. So this H+ that we produce in our solutions, in reality, it's not going to really stick around. It will find a water molecule and join up with it. The result is this H3O+ polyatomic ion, which we call hydronium. We can kind of use these interchangeably, H+ or hydronium, or even just calling this a proton, right? Because that's what an H+ ion actually is. One proton, no electrons, no neutrons. So we can kind of use these interchangeably. The reality is that we have hydronium, but sometimes you'll see us use H+ as a shorthand. We can have a quick review of acid nomenclature. For all of our compounds, we'd like to have a set of naming rules so that one chemical formula matches up with exactly one name. The way that we do this is we need to think about what our hydrogen is combining with to form our acid. These are molecular compounds, but they are built kind of based on their charges like ionic compounds are. And so even though these are not really ionic compounds, the chemical ratios are going to be dictated by the charges. And so all we need to know is what is combining with our hydrogen. Is it some element as an ion? This is called a binary acid. Our naming rule is hydroic acid. Here H2S is binary. We can call this hydrosulfuric acid. The other option, we can have our H+ combined with some polyatomic ion to form what's known as oxyacids. Depending on the type of polyatomic ion, we're going to have two different names. If our polyatomic ion ends with 8, we can change this to ic acid. So hydrogen combined with sulfate, we can call this sulfuric acid. Alternatively, if the polyatomic ion name ends in ite, we can call this us acid. Here, sulfite can form sulfurous acid. Notably, we have no indication of how many H's are needed. We know that because we know the charges. We can just say sulfuric acid, and we'll know that there are exactly 2 hydrogens because sulfate has a -2 charge. We can have another example here. Here we have acetic acid. Well, our plan in general is to write the H first in our chemical formula to give some clue that it is kind of an acid. HC2H3O2. This can be our acetic acid. If we're thinking about organic chemistry, a lot of our organic chemistry acids have that carboxylic acid group that we mentioned a few weeks ago. Our carboxylic acids have this COOH functional group. Well, if we're writing out our acid in terms of the functional groups, in terms of our organic chemistry, we can write this maybe not starting with the H, but we can write it as kind of our shorthand organic chemistry notation. CH3 for that methyl group, COOH for that carboxylic acid group. Both of these are acceptable chemical formulas. Just, well, if we're thinking about this in terms of maybe more general chemistry or in terms of organic chemistry, we can gain a little bit of a different intuition by writing out our chemical formulas different ways. The first way we have an acid we include because we have the hydrogen to start with. The second way, we're cluing that we have an acid by including this carboxylic acid kind of functional group ending. We can also introduce a definition for bases. The Arrhenius definition for bases are going to be compounds that dissociate to produce OH-. Here we have sodium hydroxide. This is a completely soluble compound. It will produce sodium ions and hydroxide ions. Aha, that's why it is a base. Some general properties of bases: they tend to taste bitter. This is an evolutionary response. Bases are generally not good to consume, and so we've evolved to not want to eat them. They can feel slimy on your skin because they can dissolve oils. They can dissolve the oils on your skin. And okay, we can also have some indicators here. Litmus paper might turn blue in the presence of bases. When we have acids and bases together, they will react with each other. Acids are going to be acidic, bases are going to be basic. They can react to neutralize each other in terms of their pHs. We haven't mentioned this yet. pH is a scale for determining how acidic or how basic something is. And so acids are things with a pH less than 7. Bases are a pH of things greater than 7. Neutral solutions have a pH of exactly 7. Acids and bases will neutralize and tend to create solutions with a pH closer to 7. Here is our example. Hydrochloric acid neutralizes sodium hydroxide. We get to produce sodium chloride and water. This is typical. We're going to have a net reaction of, well, some salt plus water. If it's a soluble salt, our net ionic equation is just those H pluses and those hydroxides producing water. We can introduce an alternative definition for acids and bases, maybe a slightly more inclusive definition for acids and bases. Bronsted-Lowry acids are going to be compounds that donate a proton. Bases are going to be compounds that accept a proton. And so we can start to think, well, these appear together because we're going to have an acid donate the proton towards our base. Here's an example, HCl and water. These will react, producing our hydronium and our chloride. Well, how did we get here? We need to send this hydrogen ion from our HCl over towards our water. HCl is donating a proton. This is an acid. Water is accepting a proton. This is a base. There we go. Not too bad. Another example, you have ammonia. We had this on our list of bases. Maybe now we can see why that's the case a little bit more clearly. Ammonia reacting with water, well, will produce NH4 plus and hydroxide. To get here, this proton has to be sent over from the water to the ammonia. Ammonia is accepting a proton, it's the base. In this case, water is donating a proton, it's the acid. A note, water is either an acid or a base, depending on the context. This is known as amphoteric. Notably here, in our Bronsted-Lowry definitions, we're having an acid and a base always combined together. We can also have some notation for our products. Once our acid reacts, it donates a proton. It will turn into the conjugate base. Our conjugate base is the molecule formed after our acid has performed its acid duties and given away that H+. Likewise, we can think about the product after our base accepts an H+. It will turn into the conjugate acid. We can call these a conjugate pair, right? A conjugate pair will be one reactant and one product. One will be an acid, one will be a base, one will be regular, and one will be the conjugate. So for example, ammonia, this was our base. After it acts as the base and accepts a proton, it turns into NH4+. NH4+ is known as ammonium. This is our conjugate acid. These two form a pair, and notice here, they're only different by the addition or subtraction of an H+ ion. So the chemical formula, we've gained a hydrogen, we've increased our charge by 1. Likewise, HCl and Cl-, hydrochloric acid acts as an acid and donates away that H+. What's left behind is this chloride. HCl is the acid, chloride is its conjugate base. We have an acid and a conjugate base. One is a reactant, one is a product. One is regular, one is a conjugate. The only difference is, we've in this case, removed an H+. The chemical formula is 1 hydrogen less and 1 charge less. We can get some practice here. What is the conjugate acid or base for each? Take a moment, see if we can get it. HF is an acid, hydrofluoric acid. If we remove 1 hydrogen and we lower the charge, we can form the conjugate base, fluoride. H2SO4 is an acid, sulfuric acid. If we remove 1 hydrogen and remove 1 positive charge, we can form hydrogen sulfate, which is the conjugate base. Hydroxide is going to be a base. It will like to gain an H+. And so we can form a compound with 1 extra hydrogen and 1 extra positive charge. This is going to be just H2O, just water. Here, water can be our acid. Hydroxide can be its conjugate base. Or vice versa. Hydroxide can be the base and water is the conjugate acid. Lastly, we have bicarbonate. This is amphoteric. Can be either an acid or a base. If you want to have bicarbonate as an acid, we can have carbonate as its conjugate base. Or if you want to have bicarbonate as a base, we can have carbonic acid as its conjugate acid. We can have one more definition of acids and bases to discuss. Lewis acids and Lewis bases. This is a concept we saw previously in our inorganic chemistry, our coordination chemistry, where, an acid in the Lewis definition is going to be an electron pair acceptor. A base, in terms of Lewis bases, will be an electron pair donor. In Lewis acid-base chemistry, we're going to be forming covalent bonds. We're going to be moving electrons around, usually to form a new, bigger molecule. Here's the example we saw previously. Ammonia can be a ligand. It has this lone pair. Cobalt-3 can be a Lewis acid, and it's looking for some extra electrons. we can form a new bond, turn this lone pair into a bond, maybe it's this one, by sending those electrons over, using it to glue these atoms together. Here, cobalt accepted those electrons, it's a Lewis acid. Ammonia donated those electrons, it's a Lewis base. And if we do this 6 times, maybe we can form this hexaamine cobalt-3 complex ion. All right, we have our definitions. Now we want to start to think about our acids and bases in the context of equilibrium, which will allow us to do some nice calculations. We said water is amphoteric. Water can ionize with itself. Here's that reaction. Water plus water forms hydronium and hydroxide. One of these waters is an acid. One of these waters is a base. We can form both the conjugate acid and the conjugate base in a single reaction. Turns out this is an equilibrium process, a reversible process, where the equilibrium it is going to reach is dictated by this equation for the equilibrium constant. K is equal to our products divided by our reactants. But recall, we don't need to include anything in the liquid phase, so it's just going to be the concentration of hydronium times the concentration of hydroxide. We give this equilibrium constant a special name. We call this Kw, and we can measure its value. At 25 degrees Celsius, Kw is equal to 1.0 times 10 to the negative 14th power. Excellent. This will tell us if we have pure water, what is the amount of H3O plus, what is the amount of OH minus at our equilibrium. In fact, we can solve this by recognizing in pure water, we have equal amounts of H3O plus and OH minus, right? Based on the balanced reaction, based on the stoichiometry. We're starting with only pure water. We need to form a 1-to-1 ratio of our two products. We want to save some time. I'm just going to call this concentration X, and we can say that Kw has to be equal to X times X. And in fact, we know the value of Kw. We can solve this. Our concentration has to be 1.0 times 10 to the negative 7th power. Our units here get to be molarity when we're using our equilibrium constant. What's nice here, our Kw value, this equation for Kw, it's true when we have pure water. It is also going to hold true in any aqueous solution. We'll talk about why that's the case maybe later on, but for right now, maybe you can just trust here, our Kw equation is going to be true for any aqueous solution. So if we have a known concentration of hydronium, we can use that to solve for our concentration of hydroxide. And so here we go. We can do a little bit of algebra. The amount of hydroxide in this case is 4 times 10 to the negative 13th molar. And as promised, we can use H3O plus and H plus somewhat interchangeably. When doing these concentration calculations, we can see that our numbers are oftentimes very, very small. Right? The concentration of hydronium or hydroxide might be on the order of 10 to the negative 13 or 14th power. Well, we can make our numbers more convenient by introducing the pH scale. The pH scale is a measurement for the amount of H3O plus, but we've changed it to be a logarithmic scale. Every 1 unit of pH is a 10 times different concentration. This condenses our concentrations, which range from maybe 14 orders of magnitude, down to a pH scale, which ranges over maybe just 14 numbers, from about 1 to about 14. We have 2 equations to convert back and forth, and we have some metrics for when things might be acidic. Okay, pH less than 7 for acids, H3O plus greater than 10 to the negative 7 molar for acids. two different ways to decide if something is acidic. We can see this scale visually. We have a pH scale about 0 to about 14. Very, very acidic to very, very basic. Right in the middle is pH 7, which is neutral. And we can see some examples of substances on this pH scale. If we want to measure the pH, we have a variety of ways of doing that. We talked about litmus paper, pH paper. Here we have universal pH paper, where you can drop a little bit onto the paper and it will change colors depending on the pH. We can also take some measurements with digital pH meters. We'll talk about how these work in a few weeks, but we can do some electrochemistry to determine the pH. A fun thing that you can do at home. Turns out this molecule that makes red cabbage, this nice purple color, is pH sensitive. You can make a pH indicator molecule using cabbage. If you have a very acidic solution, the cabbage compound will turn this nice pink. If you have a very basic compound, that cabbage compound will turn a nice yellow. If you don't mind the smell of cabbage, yeah, try this out. There are other ways of doing this as well, right? We can have indicator molecules, maybe that we've used for titrations in the past, will tell us generally, are you above or below this kind of turning point? Whatever project we're doing, we might choose a different method for measuring or indicating that pH. All right, one last metric here. We can also introduce the pOH scale. pOH is analogous to pH, except it's flipped on its head. The definition of pOH is the negative log of the amount of hydroxide. And so for pOH, we're going to have, well, bases have a low pOH, less than 7, and acids will have a high pOH, greater than 7. What we end up with are these 6 useful equations based on the definition of the pH, the definition of the pOH, and the Kw equation. One extra equation here, we can relate the pOH and the pH to each other. This is derived from the Kw equation. We end up with pH, pOH, sum together to equal 14. I'll give you these equations, but we do want to be able to use them. With 6 equations and only 4 measurable quantities, if we measure any one thing, there's going to be multiple ways of figuring out everything else. So lastly here, we can do some practice problems. What is the pH of a solution where our H plus is this concentration? What's the amount of H plus? What's the pH? If we measure one thing, can we figure out everything else? For question A, we measured the amount of H plus. We're trying to find the pH. Seems like equation 3 is good here. Select the equation, plug it into the calculator, get your value. For the sig fig rule, we have a note down at the bottom. We want the decimal places in our pH to match up with the total sig figs in our concentration. Right? A new sig fig rule for a new operation. For question B, it seems like this is a good equation to use, number 4 on our list. We know the pH. We want to find the amount of H plus. Let's have the number of sig figs in the concentration equal the number of decimal places in our pH. For question C, we don't have an equation to go directly from amount of hydroxide to the pH, but a few strategies could work. We can first figure out the pOH and then figure out the pH. That's certainly a good plan. Alternatively, we could figure out the amount of H plus and then figure out the pH. Both strategies could work, and maybe there's even more. We have an excess of equations here. Regardless of the path that we take, we should get this final answer, 7.68. We can look at this conceptually, see if we can check our work. The pH of a solution where H plus is 2 times 10 to the negative 8 This is a little bit smaller than 10 to the negative 7, which means our solution is going to be a little bit basic, which is the case. We see a pH slightly above 7. Cool, checks out. Our second solution has a pH of 2.10. A low pH means it's acidic, means we expect to have a large concentration of H+, and we do. 10 to the negative 3 is large compared to the neutral solution, which is 10 to the negative 7. And lastly, our hydroxide concentration is a little bit big compared to 10 to the negative 7. And so we're expecting a solution that's slightly basic, our pH just slightly above 7. Again, checks out. That is what we expect. All right, and there we go, wrapping up our first video here, introducing our acid-base definitions and introducing 6 nice equations to do some calculations based on how acidic or how basic our solutions might be. Thanks for being here. Please let me know if you have any questions, and I look forward to seeing you all in the next video.